So, last time we saw the solution for a given G on the boundary of a disk, continuous, of harmonic extension of this function inside. Okay, so today we are interested in the following problem. So suppose that now we have G given, the ball, say, of radius r centered at 0, say for simplicity BR here, given. We look for an expression, look for solution to U is 2, C0, harmonic, inside. So we are in any dimension here. Maybe I will make all computations in three or more dimensions. And then U equal G on the boundary. Remember, as I said several times, this is classical way to attain the boundary condition. It means limit as x goes to 1, say x in the for any y. Okay, so this is what we would like to study today. But let us start with some more general, so this is the problem generalization of last time. Last time we made this in 2 dimensions, you remember? Last time was and we used Fourier series expansion. Do you remember? Mm-hmm. Okay. So today it will be, maybe I will. Okay. This case has been treated last time, so I will confine to n larger or equal than 3, maybe in the computations. Okay. But before, so this is the aim. But before doing this, let me go back to some general formula. Remember, okay, suppose that omega is the bounded smooth open set, and suppose that U is harmonic in omega. Then we had, if you remember, we had a representation formula for any x in omega. There is a representation formula that we found some lectures ago, which is of this form. It is a U of x equal to minus U dgx d omega minus gx u. Please check this formula if you can find it in your notes, so that we check the formula of the notation is, so this is for any x in omega, and the new omega is exterior, unit outward, normal, to omega. Outward to omega. Okay. I think this is, did you find it? If the signs are correct, there is a minus here?
Yes. Yes.
Minus u. Okay. So we have this formula, and we would like to start from this. This is a starting point. Not only for showing existence of a solution, but also for giving any sort of explicit formula for the solution itself. So, starting point for giving an expression the solution of this point problem here. Okay. Now there is an unpleasant property here. There is an unpleasant fact in this formula here, is that, okay, usually the formula that we want, since we are giving a Dirichlet condition, this is okay. I mean, is u on the boundary, so u must be equal to g. G is given, so this is okay in some sense, no? Because if I put g here, then this is a datum of the problem. This is another stuff. I mean, it's fundamental solution. G of x, y, remember, is some constant log into dimensions, or times y and minus 2 in larger or equal. Larger or equal is the fundamental solution for the Laplacian. But here, however, we have a problem. There is the normal derivative of u, and we don't like it. Because this involves not only u itself, but when you compute it, it involves also the values of u inside omega, not only the values on the boundary, because you're doing a normal derivative. So this is something that you have to avoid. Otherwise, we are not able to give a sort of formula. We would like to have u here, right? So some sort of u. Okay, so now we introduce, in order to give an expression of u as integral of the boundary of u itself times something which is independent of u, say, independent of u, but not, I mean u, but not its normal derivative, just u, independent of u, maybe depending on omega, but not depending on u. We want, in order to give an expression, eliminate du over the new omega in this formula in 1. Okay, so now we give a definition, and there is essentially a unique way to do this. There is only one way. So I give you now a definition of corrector, maybe, and you will see how we can do. So definition, so given corrector, maybe, so given x with a note, if it exists, of course, by Vx. Solution. To, say, Vx in C2 omega bar. See? This is then this must be harmonic inside, and Vx equal Gx on the boundary of omega. This is not a singular. This is not a singular boundary condition, because this is singular. So this means Vx of y equal Gx of y for any y on the boundary of omega. X is inside, so this is singular only on the diagonal when x is equal to y. No? It is singular only when x is equal to y, but x is in omega and y is on the boundary. So therefore this is a smooth object as soon as y is on the boundary of omega, because it is automatically different from x. Okay, denote this by Vx. Yes, this is Vx. Okay? Okay. Now you see, there is only one way to arrange this term, because now we have some Green's identity. Please look Green's identity. If we let me recall, I think that we wrote this maybe the second lecture, first or second lecture. So it was something like this. Suppose that U and V are harmonic in omega. Okay, suppose that and smooth enough, smooth, say C1, smooth up to the boundary. See. Then we have the following relation. This volume integral here. So please check also this formula and the signs in particular. U Did you find it? Is it correct with U here and plus U here?
No, sorry. It's the left, right?
Here we have
Left side is
U.
Yes. So you shift.
Yes.
Okay. U Laplace V minus V Laplace U.
Yes, gives this.
Okay. U Laplace, yes, thank you, sorry. U Laplace V minus V Laplace U, and then there is U as U, minus V Laplace U. Okay, and the signs are correct now. Yes. Thank you. Okay. Now you see the way to destroy, in some sense, the presence of this term here, because now we have that U. So this is capital U, but it's a generic U, okay? So now we apply this formula to our small u, And to this object here that we don't know anything about, but it is harmonic. If it exists, it is harmonic. Okay. This means that the left-hand side is 0, because v, so we apply this to u, and vx. Okay, we just apply this. So what happens? It happens that they are harmonic. So this is 0, this is 0. So the left-hand side must be 0. Fine. So now this means that the right-hand side must be 0. And therefore, u, small u, dvx over d nu must be equal to integral vx d small u over d nu. Okay. Oh no, maybe I no, sorry, not to u, not to no. This is wrong. I want to exchange the derivative here. Sorry, so I have to take u and gx. Sorry, gx. Okay, so gx is harmonic. Gx is harmonic.
I think Vx was correct.
Vx was correct. Yes, Vx was correct. Thank you. Vx was correct. So you see, here we have u dvx d nu omega must be equal to Vx, but Vx is equal to Gx.
Yes.
So this is the Gx, thank you. Du over d nu omega. So there is only one way to do this. You have to introduce this object in order to simply move the derivative from here to here. So in this way, now we do this. So we have now this representation provided that we are able to find Vx. So we mark, provided we have Vx, solving this, provided we have Vx, we deduce that ux from 1 and 1, 2, say, from 1 and 2 ux equal minus integral boundary of omega u dgx d nu omega minus u something like what did I do? U dgx, this is okay. Oh, I have to move this from here to here. I think that this way I found something that I don't like. This was correct, no? Attraction of Vx. Vx equal G. No, but I cannot, okay, but then here I have minus u dvx, right, over the nu omega. Correct. No? So, dh minus, do you agree? Do you agree with this? Okay, here I have the derivative. This is gx, because vx is equal to gx. Otherwise, in general, it is vx, so I have to move the normal derivative on vx. So now there is, you see, I just have this expression now, u, and then there is the normal derivative of something. Fine, so the normal derivative of something, so let me write it. Now this something, let me denote it by, so definition. Gx omega of y. Let me denote it is gx of y minus vx of y. Where is this object defined? So this is a definition. This object is defined for any x in omega, as we said at the moment, because x was taken in omega. Y, well, in principle, y could be also, I mean, Vx of y is defined in omega bar, so for any y in omega bar, but x must be different from y, otherwise there is a problem. Okay? So this is called, I think, the green function for omega. Green function for the open set, for the bounded C1 open set for omega. Okay. So now what do we have here? We just have d over dn omega gx omega dhi minus 1 of y, dhi minus 1. Do we agree? Or are there problems with this formula? So let me summarize. We start from the Green's identity, so that we have this expression. We want to move this on the other side. But then, in order to have u here, so that there is only u multiplied by something, as it is written here. And this something must be independent of u, possibly. So how to do that? Okay, we recall this identity, and we are more or less directly forced to solve this problem in order to put the derivative on Vx here. There is only one way to do this. There is no ambiguity. Okay, after this sort of computation, where are we? So we have the following remark, that for any x in omega, if u is harmonic, ux must be equal to this expression here. Okay? This is sort of implicit, because to have this, we have to solve this problem, and we don't know how to do. No? This we don't know. Suppose that we are able to do. If we are able to do, then we have this, and then we have for a harmonic function this expression. Now this will be g at the end, small g. No? So the right hand side at the end will have small g here, then an object which is what? It is the fundamental solution that we have found, depending on the dimension, the norm, etc. And then something else, and this something else, if you look at it, depends on omega, but does not depend on u. No? So this object here I put an omega here in order to recall that we have to solve a problem in there is a dependence on omega here. Not on this, but because of this.
Okay, I just have a question. Are we solving it for omega or for the whole? For any omega?
This is a general, just maybe a little bit formal because we don't know anything about this.
Yeah, I understand.
There are some assumptions. In particular, we have an assumption on boundedness of the open set and say C1 of its boundary. The point is that this seems to be a nice representation formula for what we would like to be the solution. When are we able to really find this object? This is the second question. Maybe it's your question. No? So this is general for any omega.
Because at the beginning you state the problem in a ball.
Yes, at the beginning. But then I said, let me come back for a moment to a bounded smooth open set and let's do this kind of computation. Then I will come back to the ball. Because for the ball, we are able to find this. Because for the ball, we were able to find this, essentially.
But if we are able to solve it for the ball, then simply, since in this problem, here Gx, or the fundamental solution, is harmonic except at the point of singularity, right? So we can isolate it and then try to find a solution for the ball, which we already know, and then just the sum of both will be the solution, I guess.
For omega, no.
We'll have,
no, this doesn't work. We can, I mean, you need here some special geometry, at least as far as I know, to find Vx, which means to find this object here. You need some
No, I'm not saying that we are able to find Vx. I'm saying that once we are able to solve it for the ball, we can use the solution of the ball to solve for omega.
Yes, this is the Perron method. This is the Perron-Wiener-Breloch method. But it's quite involved. Once you are able to solve it for the ball, you're right. Then there is a way to solve for any omega with maybe some assumption, some weak assumption on the boundary, using a sort of maximal subsolution and minimal supersolution constructed using the solution that you know for the ball. That's true. No, but today what I want to tell you is first of all that moving from this expression to this is quite natural because of this observation. So we are reduced now to this problem, and we are reduced to solve another problem like this. Okay? And now the hope is that maybe for some special omega we can do. Now, you see somehow why I call it corrector? Because it corrects this. In some sense, if omega is the wall of Rn, suppose that, now it cannot be because it is not bounded, right? But suppose for the moment that omega is Rn, we are looking for a smooth solution which is harmonic on the wall space and which must be equal to this on the boundary of the domain. Okay, there is no boundary in Rn. But we know at least that the fundamental solution is infinity, is going to 0 at infinity. No? So, formally, one could think that this should be Vx equals 0 at infinity, somehow. But then, Vx identical equal to 0 is okay. So for Rn, what I want to say that this seems to be a modification for an omega to what previously was this for the wall space. So I correct this expression for value for the wall space with something. This was the first remark. The other remark. Yes, see, the other remark was, now let us go back to the ball, and for which kind of open sets is it possible to do this computation? And I would like to give you an exercise to be done after what we will see for the ball. So this is, okay, so let me write it here, x equal this. So this I don't need, this I don't need, this I don't need, just this. This I need. So maybe it's time also to give a name. So this has a name, but in the explicit representation of our possible solution, there is no gx, but there is its normal derivative. So this normal derivative has another name. So this is a name, but then for its derivative we have another name, which is called Poisson kernel. So maybe let me call this, okay, so definition. This is defined, so this is called Poisson kernel. Poisson kernel, so y is on the boundary of omega, x is inside, and we have this this expression. Okay. Now, let us do some computations for the ball, and then another geometry for which we can do the computation. Do you know which other set? The upper space, the half space. So home, I ask you to do. I ask you to redo the computation that we are going to do now. So home, study this problem here for omega equal xn larger than 0. Okay, this is a particularly simple geometry. It is just into dimension, it's just a half space, a half plane, or a half space in any dimension. That's okay. There is a minor difficulty because this is not bounded. So maybe one should check that all the integrals he is going to write are now integrals on an unbounded set, and one has to check that these integrals converge. And maybe on G, since we have this unboundedness, G say is continuous on the boundary of the half space and bounded also, for simplicity. Okay. Okay, so we have introduced a couple of new objects. One is this, and then there is its normal derivative, which it is exactly what we need in this expression. Okay. There is a minus apparently in front. I don't know. Should check the signs. Sorry. Maybe here there is a minus. Sorry. So that now I check. now the signs. So for MX, I think that probably here there is a minus.
Yes.
Just let me check. There is a minus. Okay. So that we really have this sort of kernel with a plus. Fine. So now from now on, today, we will try to do the computations when omega is the ball. So this was general, bounded the smoothness, etc. From now on, fix this. Okay. So, and the idea is clever because one has to guess who could be. So we have here there is 0 for simplicity. Then we have x. See. This is R, a ball of radius R. This is X. And now the problem is how to, there is a guess. There is a guess on who could be a reasonable Vx. And this is based on sort of reflection principle in the sense that one looks for Vx of a special form. One looks for Vx. Have you ever seen this kind of Vx? Maybe in physics, because it is called the method of images in physics. I think the method of images, images. No, physics in electromagnetism. Never seen it. So there is a guess, then a posteriori it works. So I tell you which is the guess. So you are looking for a harmonic function inside here. And which kind of harmonic functions we know for the moment? We know that this is harmonic with a singularity at x. So we cannot take something like that, because that will be singular at x, and x is inside omega. While we are looking for a solution which is smooth, very smooth inside omega. So why don't we look for Vx of the form gx, but not x, another x. So let me call this gx bar. Well, now, if you're, gx bar is what? Is an harmonic function singular at x bar. So given x, maybe we can imagine another x bar depending only on x, which is outside. No? So if there is some x bar outside, and I consider this function, then this is harmonic surely here. And this is moved up to here, right? So the idea is exactly this one, is to look for an harmonic function of this form, okay, but with this x bar, which is not x, it's say specular image, it's sort of specular image, and it is natural somehow to guess where could be this x bar. What do you think? If x is here, I'm looking for some x bar which is outside. Where do you think where you would try the first guess to put it in order to do some simple computation? Where you should put your x on the same direction, somewhere. No? So maybe x bar here. We don't know exactly where. And now, so x bar in the same direction as x, so x bar equals some multiple of x. T is not known at the moment, but a posteriori it will be, we will see, and then here there will be some adjustments, some maybe some object here, some C. Okay. So a posteriori we will see that x bar equal to r squared divided by x squared x is correct. So you see, this is T, sort of T. And this, this is a posteriori, so I will do the computation. So we are looking, one looks for, so let me rewrite the problem. This is just a guess. There is not, for the moment, we don't know if there will be a solution, right? In particular, because it's difficult to imagine that this object, which has a singularity here, right? Has a singularity here, also satisfies that its boundary condition on this ball is exactly the boundary condition of this gx. The difficult part is to adjust the boundary condition. No? Okay, so let me try to tell these things. So we try to find a solution Vx of the form Vx equal C gx bar in the unknown C and x bar. So this is just an attempt that we do. We don't know where it will go, but let's see. Just one comment on this map here. Can you see what happens to this map? If I am, just for simplicity, suppose that just for simplicity, okay, suppose that this map here, what happens when x is inside, but suppose that for the moment x is on the boundary, and consider this map. So this map is exactly the identity on the boundary, okay? Just to remember, so x bar equal x on BR. Then, if I'm very close to the origin, where is it going, this? It goes very far, right? So it goes to more or less to infinity. So here I am the identity, here I'm close to the identity, but as soon as I'm very close to the origin, the image of points here close to the origin are very far. In some sense, this is called the reflection. So if you have a charge here, and you want to reflect it with respect to this, which is not flat, of course, this point is called the image charge in physics. So when the charge is exactly the center, you are at infinity. Have you ever seen this map? So do at home on compute okay.
But X bar is out of the whole, right?
This I mean, is a map which is defined everywhere, apart from the origin, if you want. Out of the origin, now, yes, we're starting with X inside, but look now at this map by itself. As soon as X is non-zero, this is defined also outside. Okay. Okay. So, let me see. So we are looking for this. So this means that we are looking for some constant C multiplied by, we are doing the computations as I said. So computations from now on n larger or equal than 3. The computation I'm going to do, please do the computations in n equal to 2. Okay. Remember that n equal 2 has been already done last time. So let's see this. What is this equation saying to us? So it says C multiplied by, now we are in dimension n larger or equal than 3. So we have y minus x bar to the n minus 2. Okay. This we have this identity. You see. So it is clear that this. Okay, let me write the variables. Vx of y must be equal to c that I will find. I will give you the expression of c. I will find it. The expression of C is independent of Y. Independent of Y. G x bar of x. So x bar of x, and also x bar is independent of Y. Okay. So how do I have to interpret this equality? Let me repeat it. There is an independent variable, y here also, but see, turns out it to be independent of y. This g, of course, depends on y, but x bar is independent of y. Okay. So, you see, as soon as x bar of x, as soon as x bar of x is outside, this quantity is smooth inside up to the boundary, and this is also harmonic in the ball. So this is okay. These two are okay. But now we have to arrange the coefficient here in order to make also to fit this last boundary condition, which is the difficult part. Is it okay, or is it clear what I'm trying to do? No. Maybe I'm not clear.
Not clear about the stuff.
This is just, I mean, a try. You try a possible Vx. It's a little bit formal up to now, but then at the end you really end up with something which is rigorous. You can check that your Vx at the end satisfies all these things, and therefore your X at the end will be really of this sort. So now, So we have this, so we have to arrange also, to force the validity of this. So this must be equal, so for any x in omega, this must be equal to this, right? So this means 1 over y minus x to the n minus 2 for any n, for any y on the boundary below. This is condition this condition here. So given x in omega, so the problem now becomes, let me rewrite the problem, let me erase everything, let's see, maybe I keep the C of x maybe. So given x, we look for C x bar of x such that for any y on the boundary of the ball, Cx multiplied by the Green's function singular at x bar must be equal, so C of x, if you want, let me write it as follows, C of x equal y minus x bar to the n minus 2 divided by y minus x to the n minus 2. Or if you introduce k equals c over n minus 2, equivalently k must be equal to y minus x bar divided by y minus x. Okay? For any y. So what do? We start to try to fix the solution looking at two special choices of y. The only choices the simplest choices of y in order to somehow...
This one? Simple choices in this one?
Yes. So, why don't we try what happens here and here? So, let me call this y prime. So, y prime is simply in between x and x bar. No? There is and then the opposite is y second. Okay? X bar equal t x t of xx. So, okay, now, so what do we have? We have y prime minus tx divided by y prime minus x. This must be equal also to k, but k, must be independent of y, no? So when I insert y prime, I get k, but this k must be the same also when I insert y second. Okay. So okay, so I have this at least. Let me see what happens. y prime minus x is this length, which is r minus, so y prime minus x, it's easy because it's r minus normal x. Y second minus x is also easy because is equal to r plus normal x. Okay? So now y prime minus tx, so this is x bar, y prime. Okay, and then okay. So this is
tx minus r.
Yes, exactly. Y prime minus x is equal to sorry, c is positive. We look for c positive. Okay. So as you were saying, this is tx. So the norm of this minus r, correct? On the other hand, the distance between y second and tx is just tx plus r. Okay. So now I have to insert this information here and to see what happens.
Tx and tx. Y prime minus tx.
This is y second.
Minus tx, right?
Yeah, y prime minus tx.
Y prime
Minus tx. The second.
So yes, sorry. Y prime here, I think, is y
Yes.
prime minus tx, and
also-
there is also tx. Yes, thank you. Okay, so now I do the computations. I just substitute without trying to, so tx minus r divided by r minus x must be equal to tx plus r divided by r plus x. So what do I get? So t x minus r multiplied by this must be equal to tx must be equal to this tx plus r multiplied by okay. So let me expand the calculation. So we have tx r plus tx squared minus x squared minus r must be equal to tx r minus minus tx squared plus r squared. Is it correct? Are you following this? Seems correct.
Minus
no?
rx.
So minus r. That's it.
First 10.
Okay. So this means t equal r squared over x squared. And as you see, no? As you see, t is independent of y. So it is of this form here, T of x. So it's just a constant. Once x is fixed, you can think it as a constant. So I am moving along this direction. Okay, so now that we have t, we also have k, right? Because k must be then equal. I mean, this does not say. Let me be clear a little bit. I mean, this does not say that I'm sure I'm solving this. This says only that if a solution exists, it must be equal. This t must be necessarily equal to this. But this does not say the solution exists, because the solution is much more stringent. I have to satisfy this condition for any y on the boundary, not only for this y and for this y. So in principle, I just, again, I'm guessing what should be the solution, but it's not clear it exists, because then once we have found the solution fixing this y and this y, then we have to check it satisfies for all y. Otherwise, no. So k must be equal to y minus r squared x squared x divided by y minus x. Okay. Let me check that my t is okay, because otherwise, if I so t is yes, this t is okay. This t is okay. So this t is okay. Now k what should be k again? This k should be independent of y. So
This is equal to r of x.
So we can again insist with taking y prime. See? So if we insist by taking y prime, this k must be this divided, sorry, no, must be y this r minus x, and then we have y prime minus tx, this tx minus r, tx minus, and t is must be that one. So this means that so we have r squared divided by x squared times x minus r divided by r minus x. Correct, huh? I just substitute my t, which was r squared divided by x squared, tx so y prime minus x bar is this tx minus yes, y prime. Okay, and then so let's see, I can put an r in front of everything. So we have r over x minus 1 divided by r minus x. So it seems to be simply r divided by x. Okay? R divided by x. This is k. Okay, so if a solution exists, if so what is summarizing? So if a solution of our problem exists, if such a Cx and x bar exist, then they must be equal, so C bar, so the relation between, no sorry, C, not C bar, C. If C and x bar exist, then C must be k to the n minus 2, and k was this, so necessarily this must be r over x to the n minus 2, comma, and x bar must be r squared over x. Okay, is this clear up to now? It's not so easy, yeah? It's not so easy. So, in order to check that our problem has a solution, now we have to check that with that choice of C and with that choice of x bar, this is satisfied for any y. Okay? I could leave this U to this at home, maybe. So home for me, I think it's convenient to go back to the K representation, okay? So home, I think that you should check with that choice of C and x bar, show what? That k squared, if you want, k squared y minus x squared is equal to y minus x bar squared over y. I think that, I mean, it should be almost immediate. Let's see. This should be almost immediate. No? We agree? K is this. So I take the squares because it is easier to develop the norms. So from one side we have k squared is what? So k was, I think that this was k, no? Okay, so k squared. So from one side, what do we find? That k squared is equal to r squared over x squared multiplied by y squared plus x squared minus 2yx. And this is what? Y is on the boundary of the ball, therefore this is r to the 4 divided by x squared plus r squared minus 2r squared divided by x squared yx. No? This is the left hand side. The right hand side is y minus x squared is y squared plus x bar squared, but x bar is r squared over x squared times x, so that is r to the 4 divided by x to the 4 multiplied by x to the square minus double product to y comma r squared over x squared x. Okay, now let's see, they should be equal, so there is r squared, which is here because y, this is r squared, r to the 4 divided by x squared is also present, it is this one, and also the other one is present. Okay. So this, I think, gives us a nice fact. So we have an explicit expression of what she was asking for, the ball. So our corrector, so for the ball, we have the Green's function. So for the corollary, so hence, so gx for the ball. Now, and then larger or equal than 3. You should do n equal to 2. Is, as I said, is, remember, is this minus our corrector. Okay? But our corrector is c gx bar of y, and the dependence of y is only here because c is independent of y, x bar is independent. Okay, so this is equal to, now there is some constant, so 1 over n minus 2 sigma n minus 1, if you remember our notation. Then we have 1 over y minus x to the n minus 2 minus r over x to the n minus 2 1 over y minus r squared over x squared, sorry, squared x to the n minus 2. I simply substitute gx, we know gx is this constant, this is the fundamental solution. Then there is the corrector, c, we found it, if there is no mistake, it's just this, so just substitute this depends on x, independent of y. This is again the Green's, the fundamental solution, but the singularity is at x bar. So the singularity is here, and x bar is this. Okay. Okay, now there is an interesting property of this Green's kernel. So this is first result. So we have to do 2 computations in order to continue our project of finding the solution for the ball. Okay, and 2 computations. One is the following, one is the symmetry. So this is defined where? Okay, for any x in BR, for any y, say wherever you want, but in Rn minus x and x bar, whatever. But okay, for any y in the closure of BR, it's okay because x is inside, y is on the but we could also, so y is different from x bar, because x bar is outside, is strictly outside, but we could also extend a little bit, writing for any y in Rn, y different from x bar and x also. But I don't think we need it, okay? The two computations that we want to do now are the following. So the previous one is the following. It's a factor symmetry of, which is not so clear from this expression, maybe. There is a symmetry if you exchange x and y. I don't know if you see it. So gx br y gy br x for any x in br, for any y also in br if you want. Of course, we could also put x in principle, we can extend x also on the closure, even x and y in Rn, provided that this denominator is on 0. Yes, this y is different from x and y different from x bar, we could extend. If you look at only this expression, okay, they are defined now also. So now I don't know if you see, it's not clear maybe from this expression that there should be some symmetry between y and x. Or do you see it, or do you imagine it, why this should be true? It is a general fact actually, not only confined to the ball. Maybe I should have said this before. This symmetry holds not because we are in the ball. I mean, it's a more general fact.
But here we have the C is defined on the ball, only for the ball, right? The constant C and the x bar.
Yes, in this case, this expression is valid clearly only for the ball.
Yes, that's why you are saying the symmetry.
Because it is possible to prove it also at the level upstairs, say at the level before passing to the ball. You have this correct, this was Vx.
Yes.
Also at that level. Okay, doesn't matter, but let's try to see why this should be true here. It's not so clear, no? That if one exchange y with x, maybe I think that this could be a good exercise. Why not? Because no, working on that. Oh, or is it too difficult? No. The expression is there. Oh. It is clear that this is insensitive with exchange x and y. What it is not clear is this, no? It's not clear that if I change y and x here, this object remains the same. But still it is true. And I leave you as an exercise. It's not a few lines of computations. Okay, other exercise on. Oh, maybe I forgot. So, exercise. Okay, so exercise. home also, so x, y, this is also very easy. They are more than exercise, are just simple remarks. This infinity in a neighborhood of any xy in Rn times Rn y different from x y gx here y is harmonic. Again with this constraint, and by symmetry. Once you have the symmetry, once you know that this is true, the same holds for this. Okay. And our home exercise also, it's interesting. Tomorrow I will do this computation, by the way, so try to do this. If you don't succeed, I will do this tomorrow. So, but I prefer to leave you to do some computation. So home, the normal derivative. So the gradient with respect to y of g x v r, where it is defined, clearly, where this is defined. So this is minus. So we have a constant 1 minus x to the n r squared. So that the Poisson kernel for the ball is just there is a minus, yes, there is a minus. There should be a minus.
The Poisson kernel is minus the...
No, yes, then the Poisson kernel is just minus this scalar y over norm of y. Okay, so and this, so once you have this, it's easy. So this is with the plus now. 1 over sigma n minus 1, r squared minus x squared, 1 divided by r. No, because now you have to take the scalar product, apart from the sign, you have to take the scalar product with the outer normal, which is y over norm of y. So here you have norm of y as a rest, which is r, which kills one of this r. So it remains only one r here. Okay? No? It's clear? No? There is only, so you eat one of the two powers here. And then there is the important x minus y to the n. So please do this kind of, try to do this computation, try to do this normal, this gradient, and hence the normal derivative on the boundary, so that at the end, I mean, we expect to have this kind of formula, no? You remember, so integral boundary of the ball. 1 over sigma n minus 1 r Just let me check before concluding. So you have to do at home some exercise. I know I don't remember the previous one, but surely this and this. And once we have this, our general expression, remember this should be in general. Just a few remarks. One remark is that these scales, this is a square length. At the numerator there is a square length. It's scaled like a square length. Here we have a length, so this scales like the length, a length. Here this scales like 1 over length to the n. Therefore the product scales like 1 to the L to the n minus 1. Do you agree? N plus 1 minus 2. Which is consistent with the fact that we are integrating on an n minus 1 dimensional object. Okay? This is one remark in order to try to remember the powers here and there, right? Next, let's see what happens at the center, at the origin, the center of the ball. This means that I take x equals 0 here. If I take x equals 0 here, I get that u0 must be equal to 1 over r sigma n minus 1. Then we have integral of the boundary of the ball. So we have u. And then here we have 0, and this is y, so it is r to the n. Okay? And so, what is this? It is the mean, the surface mean value formula. So this is also interesting because it says that surely if this formula is true, it is for the ball, it is a generalization of the surface mean value formula, which was valid only at the center. But here x is arbitrary inside. So it's a strong generalization of the previous formula in this sense, okay? Okay. So for today.